Ever really stop to think about the intricate electrical dance happening inside something as, well, every day as an X-ray machine?
Hmm.
It's way more than just flicking a switch, isn't it?
Oh, definitely.
Today, we're taking a deep dive into the fascinating physics behind X-ray systems, specifically the absolutely crucial role electricity plays in making those images possible.
That's right. And our mission today
Yeah.
is really to dig into that remarkable engineering. How we get from the plug on the wall,
That's normal power.
exactly, ordinary wall current, how that gets transformed into these incredibly precise, high-energy beams for for medical images. You
Right?
want to make sure you walk away with the most important nuggets,
Yeah.
the core aha moments, without feeling too bogged down. And
Okay.
we've got this great study guide on radiography physics to sort of guide us through it.
Perfect. All right, let's dive into the current then. We all kind of know AC, alternating current, from our wall sockets.
Right, back and forth.
And DC, direct current, from batteries. Simple enough. But for an X-ray machine, this isn't just theory, is it? It's like the foundational problem we need to solve right from the get-go.
Oh, absolutely.
So why? Why is that distinction between, oscillating AC and steady DC so absolutely critical for making X-rays?
Well, it really comes down to control
Yeah.
and, frankly, preventing disaster.
Okay.
The X-ray tube itself, it needs this perfectly one-way direct flow of electrons, from the cathode to the anode.
A one-way street.
Exactly. Imagine trying to push water through a pipe, but the pressure keeps reversing, like super fast.
Yeah, chaos.
Right? So if AC, that back and forth current, 60 times a second here in the US, 60 hertz, if that were fed directly into the tube,
Yeah.
well, it would be damaged very quickly, maybe even destroyed,
How so?
because the electrons would be slamming into the wrong parts at the wrong time,
Yeah.
literally burning things out. It just can't handle it.
Okay, so we've got this chaotic AC coming in from the wall, but the delicate X-ray tube demands this perfectly behaved one-way DC flow. How do we bridge that gap? How do we convert that, wild AC into the gentle directional current the tube needs?
Yeah, that's where the rectifier comes in. And it's really quite
A
ingenious.
rectifier. Okay.
Think of it like a one-way valve or maybe a bouncer at a club.
Uh-huh. Okay.
It only lets electrons flow through in one direction.
Mm-hmm.
Modern systems use these things called solid-state diodes.
Right.
And the really clever part here is how it works. It effectively blocks the negative half of the AC cycle.
Just chops it off.
Essentially, yeah,
Mm.
it prevents those electrons from ever trying to go the wrong way. Without this seemingly simple bit of engineering, you just couldn't get continuous, reliable imaging. It wouldn't work.
But blocking half the current like that, it feels a bit inefficient, doesn't it? Like you're only using half the power available from the wall.
That's a really good point.
Is there a smarter way to, harness all that incoming energy? Because, yeah, it feels like we're losing potential.
You've absolutely hit on a critical point about efficiency.
Mm-hmm.
And yes, thankfully, there's a much smarter solution.
Right.
It's called full wave rectification.
Cool wave. Okay.
Yeah. So instead of just, like you said, tossing out half the wave,
Right.
this system uses 4 rectifiers,
Yeah.
4 diodes, usually arranged in what's called a bridge circuit.
Okay, 4 instead of 1 or 2.
Exactly. And this clever arrangement means it converts both halves of the AC cycle into usable DC. It flips the negative half over, basically.
Ah, okay. So you get bumps of power from both the positive and the negative parts of the original wave.
Precisely.
Yeah.
And the result? Well, you get a much higher average voltage and, crucially, significantly more efficient X-ray production.
Makes sense.
We're now using virtually all the power coming in, not just half of it.
Okay, brilliant. So we've successfully managed the current, got it flowing in one clean direction, much more efficiently too. But, a gentle DC stream isn't enough power, right? For X-rays, we need serious punch. We need incredibly high voltage to get those electrons flying.
That's the next big step.
How do we crank up that ordinary wall current, maybe 120 or 240 volts, to the kilovolt levels needed, thousands of volts?
Yeah, tens or even hundreds of thousands.
That's where the ingenious world of transformers comes in, right? These devices that
yeah.
change voltage using electromagnetic induction.
Exactly. Transformers are the voltage magicians here. And the core mechanism is, it's quite elegant, really. Almost seems like magic, but it's pure physics.
How does it work?
You have 2 coils of wire, a primary coil and a secondary coil, and they're typically wound around an iron core.
Okay.
When AC flows through the primary coil, it creates a changing magnetic field in the core. And this changing field then induces a voltage in the secondary coil.
Right, induction.
And here's the simple trick. The voltage is altered just by changing the number of turns in those coils.
No.
If the secondary coil has way more turns than the primary, the voltage goes way up. If it has fewer turns, the voltage goes down.
Simple ratio.
Pretty much.
Yeah.
So the challenge then becomes, like you said, how do we get the exact voltage needed? Because different parts of the system need different things, right? You need low voltage for one part, massive voltage for another.
Yeah, you've hit on something crucial there, that need for precision and different power levels, and it leads directly into how that voltage is manipulated because, like you said, we need different settings for different scans. So we generally have two main types of transformers in an X-ray system. First, the big one, the step-up transformer.
The workhorse.
Right. As the name suggests, it massively increases voltage. Its specific job is to raise that incoming line voltage up to those kilovoltage levels, kV levels, needed for actually making the X-rays penetrate.
That's where the real power boost happens, turning volts into kilovolts.
Then, logically, we have the step-down transformer.
Yep, does the opposite.
Decreases voltage. And this one's used over in the filament circuit, right? To reduce the voltage way down just for heating the filament.
Exactly. You only need a few volts, maybe 10 amps or so, to get that filament glowing hot. You don't want kilovolts there.
Definitely not.
And then there's a really specialized, incredibly useful performer. It's called the autotransformer.
Autotransformer. Okay, how's that different?
Well, unlike the regular step-up or step-down ones with their two separate coils, primary and secondary, the autotransformer is unique because it uses a single coil of wire.
One coil does both jobs.
Sort of. It has connections, or taps, at different points along that single winding. And by selecting different taps, you can vary the output voltage relative to the input voltage.
Ah, okay.
And what's particularly clever about this design is it allows you to adjust the incoming line voltage just slightly up or down before it even gets to the big step-up transformer.
Why would you need to do that?
Well, think about the bigger picture. This is precisely what allows the operator, the radiographer, to select different kVp levels.
Kilovoltage peak, the energy setting.
Exactly, for different exams. You need lower kVp for, say, a hand X-ray, and much higher kVp for a chest or abdomen. The autotransformer is essentially the control knob for that kVp selection.
So it's like a fine-tuning dial before the main power boost?
Yeah, it's a great way to put it. It gives that crucial flexibility for image quality in different patient anatomies. It's really key for diagnostic accuracy.
Okay, that makes sense. Now let's shift focus a bit. We've got the current type sorted, we've got the voltage levels managed, but what about the quality or the characteristics of that electrical output itself?
Ah, yes, the waveform details.
Because these things directly impact the final X-ray image, right? You're talking about things like phase, pulse, voltage ripple, frequency. These sound like quality control factors for the electricity itself.
Yeah, absolutely are, and they matter a lot. Let's start with phase. You often hear about single-phase versus three-phase power, especially with bigger equipment.
Right, like in industrial settings.
Exactly. Single-phase power, like typical house power, is less efficient for something like an X-ray machine because the voltage actually drops all the way down to zero between each cycle.
A little power dip, 120 times a second.
Yeah, imagine trying to drive a car that keeps losing all power for a split second, over and over. Not very smooth.
No.
Three-phase power, on the other hand, uses multiple AC waveforms, 3 of them specifically, that are offset from each other.
Out of sync.
Deliberately out of sync,
Yeah.
So they overlap. And the result is that the voltage never drops to zero. It stays much closer to the peak voltage.
Ah, so it's a much more constant, steady power supply.
Exactly, nearly constant voltage, which makes it significantly more efficient and stable for demanding applications like high-power X-ray generation.
Okay, so three-phase is generally better for consistency. What about pulse? You mentioned that earlier with rectification.
Right. A pulse in this context is basically each burst of electrons that gets produced as a result of the rectified AC cycle.
Okay.
Remember that full-wave rectification uses both halves of the AC cycle.
Yeah, flips the negative part over.
So with a 60 hertz supply, like in the US, you actually get 2 pulses per cycle. That means 120 pulses every second.
A rapid firing of electron bursts.
A very rapid series, yes. And more pulses generally mean more efficient X-ray production.
Got it. Now, voltage ripple, that sounds undesirable.
It is. Voltage ripple is basically the fluctuation, the variation in the voltage output after rectification. Even with three-phase power and full-wave rectification, the DC voltage isn't perfectly flat. There are still small dips between the peaks of those pulses.
Like ripples on water.
Exactly like ripples on water. And just like you want smooth water, you want smooth voltage.
Mm.
A lower ripple means the voltage is more consistent, closer to a flat line.
And why is that good?
Because lower ripple equals more consistent X-ray production. The energy of the X-rays being produced is more uniform.
Okay, less variation.
Yes. And this ties directly into frequency. Modern high-frequency generators operate at much higher frequencies than the standard 50 or 60 hertz.
Thousands of hertz, right.
Tens of thousands, even hundreds of thousands of hertz. And the physics works out that higher frequency leads to significantly lower voltage ripple.
Ah, so high frequency equaled low ripple.
Precisely, which means a much more stable, consistent X-ray output. And interestingly, it also results in a higher effective X-ray intensity for the same settings.
More bang for your buck, electrically speaking.
Kinda, yeah. More efficient use of the power.
And this all ties back to the knobs the X-ray tech actually uses, right? The KV and the NO.
Absolutely. They are the primary controls. kV, kilovoltage, as we discussed, controls the speed or energy of the electrons hitting the anode.
Which determines the penetrating power of the X-rays, how easily they go through tissue.
Exactly. Higher kV, more penetration for thicker body parts.
And MA, milliamperage.
MA controls the number of electrons flowing across the tube per second. It's about quantity.
So it determines the quantity or intensity of the X-rays produced. More MA, more X-rays, darker image areas.
You got it. It's the tube current.
So the ideal scenario, electrically speaking, is to have this really stable, almost flat waveform powering the tube.
That's the goal, yes. As smooth and consistent as possible.
And what's the payoff? Why strive for that perfect waveform?
Well, the big picture here is that a stable waveform produces consistent X-ray exposure. Every pulse is like the one before it.
Okay.
This directly leads to better image quality,
Mhm.
less noise, better contrast, and importantly, it helps reduce the radiation dose to the patient.
How does it reduce dose?
Because if the output is consistent, you're less likely to get an under- or overexposed image that needs repeating. Fewer repeats mean less overall radiation.
Ah, makes sense. Conversely, if you have a poor waveform, lots of ripple.
Then you get fluctuations. Some X-ray pulses might be weaker, some stronger. This can easily cause under- or overexposure, leading to poor image quality.
And potentially a repeat exposure.
Exactly, which means more patient dose.
Mm.
So it's really clear that electrical precision and consistency are absolutely paramount. They're critical for safety and for getting a good diagnosis.
Okay, crystal clear. So let's trace the journey now. We've talked about all these components, rectifiers, transformers, controls. Let's put them together and follow the path of electricity through a typical X-ray system's main circuits. It's like an electrical roadmap inside the machine.
Sounds good. There are essentially three main circuits we need to consider. First up is the primary circuit.
Primary. Okay, where does that start and end?
This is the low voltage side of the X-ray circuit. It's where everything begins, coming from the main power supply.
A wall plug, essentially.
Basically, yes. Though it might be a higher voltage supply for big machines, its key components, kind of in sequence, are fascinating. You've got the main power switch, obviously. Then a circuit breaker, vital for safety, protects against overloads.
Always need a breaker.
Absolutely.
Yeah.
Then comes the auto transformer.
Ah, our KVP selector.
That's the one, providing that variable voltage we talked about. Then you have the timer circuit, which controls the exposure duration. And crucially, the primary side of the step-up transformer.
So the primary circuit feeds the step-up transformer.
Exactly. It prepares and controls the voltage before it gets massively boosted. It's all about control on this low voltage side.
Okay, so the primary circuit sets things up, then that voltage goes into the step-up transformer, and the output of that transformer belongs to,
The secondary circuit,
which is the high voltage.
the very
side.
high voltage side, yes. This is where the serious power lives.
And what are its main jobs?
It has two critical functions. First, it takes the high voltage AC from the step-up transformer and converts it into DC for the X-ray tube.
Using the rectifiers we talked about.
Precisely. Usually that full-wave rectifier bridge. Second, well, it contains the secondary coil of the step-up transformer itself, which is doing the boosting from volts to kilovolts.
Right.
So the process here is pretty clear. The step-up transformer dramatically increases the voltage, then the rectifiers change that high voltage AC into high voltage DC. And then it sends that high voltage DC power directly across the X-ray tube from cathode to anode to make the electrons accelerate and produce X-rays.
That's where the X-ray generation happens.
That's the business end, yes.
Okay. Primary circuit for control, secondary circuit for high voltage and rectification. What's the third one? We need electrons to begin with, right?
Ah, yes. Can't have X-rays without electrons. That's the job of the filament circuit.
Like an electron source.
Exactly. This circuit's whole purpose is to provide a controlled current to heat the X-ray tube filament.
And how does heating it make electrons?
It's a process called thermionic emission. When you heat a metal filament hot enough, really hot, glowing hot electrons literally get enough energy to boil off its surface.
Like steam from water, but electrons from metal.
That's a perfect analogy. So the components here are designed just for that. You have the step-down transformer.
Right, bringing the voltage way down.
Yeah, down to maybe 15 volts, but with a higher current, like 3-6 amps usually.
Mm-hmm.
Then, of course, the filament itself, that little coil of tungsten wire inside the X-ray tube's cathode.
The source.
The source. And finally, a device to control how hot the filament gets. Often, this is a variable resistor called a rheostat, or more sophisticated electronic controls in modern units.
A rheostat. How does that work?
It's quite straightforward, actually. The rheostat adjusts the resistance in the filament circuit. If you increase the resistance, less current flows, the filament doesn't get as hot, fewer electrons boil off.
Okay.
Decrease the resistance, more current flows, the filament gets hotter, more electrons boil off.
And more electrons means?
More tube current,
Yeah.
more MA.
So the filament circuit control, that rheostat or its equivalent, is how the technician directly controls the MA setting, the quantity of X-rays.
Precisely. It's the ultimate fine-tuning knob for the electron supply, which dictates the intensity of the beam.
Wow, okay. So, stepping back, what does this all mean? We've gone from, the simple plug on the wall through all these intricate steps, rectification, voltage transformation, fine-tuning with auto transformers and rheostats. It's incredible.
It really is.
It's not just flicking a switch at all. It's this complex, highly coordinated dance of currents, coils, and controls, all happening, flawlessly behind the scenes in milliseconds.
Mm-hmm. And if you think about the bigger picture, the broader takeaway here, it just highlights the truly remarkable and often totally unseen engineering that goes into every single X-ray image, whether it's one you might see in a hospital or one you might have had yourself.
Yeah.
It's this whole symphony of electrical components working together, meticulously ensuring safety, efficiency, and ultimately the diagnostic clarity needed by doctors.
It's fundamental to actually seeing inside the body.
Absolutely. It's not just theory. It's the practical foundation of so much medical imaging.
So for you, listening right now, maybe understanding these fundamental principles, perhaps it makes you look at medical imaging, or maybe even just your regular wall outlet, with a bit of a newfound appreciation for all that hidden complexity.
Yeah, I hope so. And it kind of leads me to wonder, considering this incredibly intricate control we need over voltage, current, waveform, just for an X-ray.
Yeah.
What other unseen electrical marvels might be operating, behind the scenes in our daily lives? Things we just take for granted, maybe in our smartphones or electric cars or who knows what else, that rely on similarly complex electrical control that we rarely even consider.
That's a great question. Definitely something to think about until our next deep dive.